So, today in this session we are going to learn refraction from a plane surface. So, suppose this is a plane surface which separates two media. One media is here, medium 1, and this is medium 2. Suppose this is, for example, this is air and this is water. So, it has been observed that if a ray goes like this, then it bends towards the normal. So, we call this angle as I and this as R. So, the light bends towards the normal water, where this is called a denser medium. So, when the light bends towards the normal, then the medium is denser. In denser medium, the speed of light will be less. In denser medium, the speed of light is found to be less than the speed of light in air or vacuum. So, optically denser medium means where the speed of light or any wave is reduced. So, for a wave, a medium is denser, that means the speed of that wave is reduced in that medium. If this is something glass or air, something like this, so what happens? The ray would have gone like this, but actually it goes. So, it bends away from the normal. So, in a rarer medium, the light bends away from the normal. In rarer medium, the speed of light is comparatively larger than this denser medium. So, rarer and denser means we can compare the speed of light in the mediums. Now, let us see what are the laws of refraction when a ray is refracted from a plane surface. That is, we call this law of refraction as Snell's law. First law and second law. Let us see now. Now, let us come to laws of refraction, that is the first law. Suppose this is a media which separates, this is a surface which separates two media. This is medium 1 and this is medium 2. The normal, this is the normal, and I call this angle as I and this R. The angle which the incident ray makes with the normal is called angle of incidence. The angle which the transmitted ray, the refracted ray makes with the normal is called angle of refraction. So, first law tells the incident ray, the normal and the refracted ray all lie on the same plane. They should all lie on the same plane. Now, second law tells the sign of the ratio of the angle of incidence to the sine of the angle of refraction bears a constant ratio called the refractive index of the medium with respect to the other. The ratio of the sine of the angle of incidence, sine of the angle of incidence to the sine of the angle of refraction, to the sine of the angle of, this ratio bears a constant ratio which is called mu, which is when the ray goes from medium 1 to 2, mu 1 2. That means this is the refractive index of this medium relative to this medium. If we write this in terms of the absolute refractive indexes, then it will be N2 by N1, where N2 is the refractive index of N2 medium 2 and N1 is the refractive index. So we can further write is that N1 sin I is N2 sin R. This mathematical law is called Snell's law. This is called Snell's law. Snell's law. This is how a ray refracts. The ray refracts at the interface of two media such that the sine of the angle of incidence to the sine of the angle of refraction bears a constant ratio, that is mu, that is the relative refractive index of this medium with respect to this. This is Snell's law. Now let us see, let us justify this law with the help of Fermat's principle, our basic idea, our basis of geometrical optics, Fermat's theorem. So now let us justify our law of refraction with the help of Fermat's theorem. Now let us take this plane surface which separates two media of refractive index N1 and this side N2. So these are two medias of refractive index N1 and N2. Now I had a point here A and I had a point here, suppose B. Now there are various possibilities that the ray will go in this way, the ray can go in this way, the ray can go in this way. So the Fermat's theorem tells that of all possible paths, the ray will correspond that path which is an extremum, minimum, stationary value or maximum. So A and B are fixed points. Suppose this distance is L1, if this distance is L2. So since they are fixed, so distance between these 2 points is also fixed. So that is, let us call this total distance as D. Now suppose a ray goes like this and then further after refraction it goes like this. So let it is incident here such that this point and the point of incident is at a distance x. So this point becomes D minus x. So distance between these 2 points, this is A, B, this is C, this is E and this is F. If I draw a normal here, this is called I and this will be called R. So this is I and this will be R. This is x, this is D minus x. So let the point of incidence of this ray be at a distance x from C. This is x, this is D minus x. Now let us calculate that if the ray corresponds this path, how much time it takes. Optical path length is how much? So the total time taken by the light from A to reach B via E is given by T will be equal to AE by velocity of light in this medium is V1 plus EB, that distance EB by velocity of light in this medium V2. Now this T becomes AE by geometry L1 and this is X. So this is Pythagoras theorem tells it is root over X square plus L1 square divided by velocity of light V1 in this medium is C by N1 plus what is EB? EB is again root over this square L2 square plus D minus X whole square by velocity of light in this medium is V2, which is C by N2. The velocity of light in any medium, velocity of light in any medium is given by C by N. So now we got this time. According to Fermat's theorem, the optical path length should be minimum or the path should take the least time. Least time means the optical path length is the minimum. That is the quickest path. So we have dt by dx equal to 0. We have to equate dt by dx is equal to 0. So first take down this note, then I will differentiate and I will calculate it further. Now let us differentiate this dt by dx. This is n1 by c times differentiation of this is root x function. So differentiation of root function is 2 root over x square plus L square, L1 square. So we have differentiated first the function, but inside this x square plus L1 is there. So again into we have 2x. So we have differentiated this term. Next come to differentiation of this term. This is constant. So plus n2 by c times differentiation of this term root function. So it is 1 by 2 root over L2 square plus d minus x whole square. Now differentiation of L2 plus d minus x square, this gives 2 minus 2x. So minus then 2 and x. So you see here 2 cancels out. Here 2 cancels out. So we can write dt by dx as here, and this we have to equate it equal to 0. This is a very important point. The derivative must vanish according to Fermat's theorem for t to be a minima. So when this is equal to 0, this side we have n1 by c. We can write n1 by c n1 by c x upon root over L1 square plus x square. That becomes n2 by c, that is we will have d minus x. So we will have d minus x upon root over L2 square plus d minus x whole square. Again C cancelled. We got n1x by root over L1 square plus x square is n2 d minus x upon L2 square plus d minus x whole square. So now you see here, sine of I is x upon this, that is x upon this is n1 sine I, n2 d minus x, this upon this is again sine r, which is Snell's law. Thus, the laws of refraction, the Snell's law, is in accordance with our basic idea of geometrical optics, that is Fermat's theorem. So, you see how elegantly the light selects out of all possible paths the path which is the quickest path, which takes the least time, whose optical path difference is the least. So, law of refraction is again the manifestation of our basic property of light, that it follows the quickest path.